Hello, everyone, and welcome to Brookhaven Lab's 75th anniversary celebration. We're so grateful to kick off our anniversary year with all the science enthusiasts joining us today, so thank you. My name is Haiyan, and I will be moderating our live discussion this evening. I'm joined by three of Brookhaven's science leaders, Haiyan, John Hill, and Allison McComaskey. Now, they each oversee large and diverse research divisions that are investigating everything from particle physics to climate science, and they'll all play big roles in shaping the lab's future. And I know our panel is excited to answer your questions about science research. So if you haven't already, please enter your questions in the live chat on whatever platform you're joining us on. And before I introduce our panel in more detail, we first want to show you a short video that will give you a glimpse inside Brookhaven Lab. We also have a special message from Secretary of Energy Jennifer Granholm to share with you. So grab a quick snack or a beverage if you want, get comfortable, keep putting your questions in the chat, and we'll be back to join you shortly.
Hello, everyone. Congratulations to the entire BNL community on this historic milestone. I mean, my goodness, 75 years. Interacting with the whip-smart scientists and engineers at the National Labs has been truly one of my favorite parts of this job. And I've visited nearly every lab, including Brookhaven, in my time so far as secretary. I really do see DOE as the nation's solutions department. And obviously the National Labs are the solutions factories, coming up with, answers to today's most pressing challenges and problems. And BNL has been, amazing in that regard, more than lived up to that reputation in its 75-year history. This is where scientists and engineers developed what's still the best treatment for Parkinson's disease. It's where you created the first single-plane PET scanner and synthesized the first successful radiopharmaceutical for PET imaging, and discovered an enzyme that helped produce mRNA COVID vaccines. I mean, all helping, of course, people to live longer and healthier lives. You're home to world-class accelerator facilities that pioneer countless discoveries in science and technology, and the future home of the one-of-a-kind Electron Ion Collider. I was actually lucky to visit some of these facilities virtually in August when I came, virtually. Brookhaven has patented the fastest mass transit technology in the world. You have discovered the perfect liquid of the early universe. You've developed superconducting magnets. BNL scientists have earned seven Nobel Prizes, from solar neutrinos to quarks. None of these accomplishments would have been possible without the people behind the science. So I just want to thank each and every one of you for your hard work and your dedication and service every single day. You've probably heard me say this before, but it bears repeating. President Biden and I are committed to supporting you and all of our National Lab staff. This administration believes in making big investments in fundamental science and innovation to solve tomorrow's challenges. And we believe in the power of science to address the biggest problems of today, and that includes climate change. President Biden is set on getting this nation on a path to 100% clean power by 2035, and Brookhaven is helping us get there through your work on offshore wind, on batteries, on grid resilience, and so much more. We're going to need your ingenuity and your expertise and your drive even more in 2022. With $62 billion in funds from the bipartisan infrastructure law, DOE is gearing up for its biggest year yet on clean energy and climate action. It's really such an exhilarating time for our agency and for our country. So I just want to thank you for your work. And I want to say congratulations on 75 amazing years. And here's to the next 75. Hello, everyone. Congratulations.
The problems that the nation faces are complex. We need science more than ever.
Here at Brookhaven National Laboratory, we are looking into little corners of the universe you can only look into at a facility like this. We are trailblazing the future.
The mysteries of matter itself are being solved here at Brookhaven National Lab.
5,000 acres, 300 buildings.
About 3,000 people work here at this facility. It's about a $600 million annual budget.
We have 3,000 to 4,000 people who come in each year to use these facilities we make available for free.
The phenomenal scientists that are here enable us to solve problems that otherwise could not be solved.
We've drawn amazing people from around the world. Science is exciting.
Brookhaven National Lab is managed for the Department of Energy by Brookhaven Science Associates, a partnership between Stony Brook University and the Battelle Memorial Institute. Ultimately, the science and technology that we do here have impacts on the economy.
What looks like fundamental science is also producing the insights and the ability and applications to do new things for society.
The beauty of this public-private partnership is that it helps us to overcome that area between a new invention and commercialization of that invention.
A lot of fundamental research has to be done before something can actually transition into a product. Here, we can solve some of these initial questions that make or break a future technology.
We are helping other people to really go to the frontiers of science.
We're trying to solve why your cell phone battery dies after a few years. We're interested in new drugs. All these problems that require science and cutting-edge science to answer them.
Here at the Relativistic Heavy Ion Collider, it's the only facility like this in the United States and allows us to recreate conditions just like what occurred in the Big Bang. For the good of humanity, we do studies like this to try to understand the way the universe works at that fundamental level.
If we understand these quantum materials, we have the potential to revolutionize energy. We have to maintain our scientific leadership, and Brookhaven's proud to be doing that by delivering the world's best facilities and for hosting the experts who are going to be leading in those critical areas for our future.
We have scientists here investigating creation of new materials. It sounds like science fiction, but it's not.
Our job is to help expand countries' energy options. Plants are the future. We're trying to manipulate plants to make more sustainable energy.
A synchrotron light source is essentially a very large X-ray machine. To give you a sense of scale, you could fit Yankee Stadium inside this ring. We focus the beam down to about 30 gold atoms. That's a world record. There's no other working microscope that can deliver that.
Batteries are going to be a huge part of the economy moving forward. We're looking for next generation batteries. How can we make them more environmentally friendly and lower cost? The whole world will benefit.
The NASA Space Radiation Laboratory is meant to study the effects of radiation so that we can design better shields for astronauts. We also have an isotope production program. We manufacture the radioisotopes that protect people from cancers in the future and can treat the people that have cancers today.
Data-intensive computing is really fundamental. Scientists produce more data than they can analyze. We develop new algorithms and tell them where interesting things are happening. We are helping people to make the discoveries of the future here at Brookhaven National Lab.
We're becoming a technical society. We need a technical workforce. We need to inspire a new generation.
The inclusive environment will allow us to become ever more diverse. This pipeline of students who are fascinated by science, that's part of the joy of this place. That's part of what we do.
There have been 7 Nobel Prizes at Brookhaven. That passion for discovery is what drives scientists. It's what makes it fun. It's why we do it. The caliber of the people who work here are the best. They come from across science and support, and every time that this laboratory does something great that has impact, all of us share in that.
We're in business to enable other people's research. They come because we have the greatest machine and the greatest scientists to work with, and they can do their research in ways they could not do anywhere else in the world.
In the early days when I was a scientist, it was discovering things that no one else had seen before. That's a really cool feeling, and the confidence that someday it's going to have an impact. Other people are going to build on it, and it's going to help make the world a better place.
All right, welcome back, everyone. Now that we've had a chance to learn a little about Brookhaven in general, I'm going to turn it over to our panel, who will share more about the science that their specific research divisions are investigating. I also want to encourage everyone watching to keep submitting your questions to the chat, because we'll begin answering them after each panelist shares their short remarks. So let's begin with Haiyan Gao. Haiyan is Brookhaven Lab's Associate Lab Director for Nuclear and Particle Physics. Haiyan, please tell us a little more about nuclear and particle physics at Brookhaven Lab.
I'm very happy to do that. Good evening, I'm Haiyan Gao, and I'm sitting in the S-Phoenix Assembly Hall at Brookhaven National Lab. S-Phoenix is a new detector under construction at Brookhaven's Relativistic Heavy Ion Collider, or RIC for short. Before I tell you why we are building the S-Phoenix detector, let me give you a brief introduction of the Nuclear and Particle Physics Directory at Brookhaven. The science mission of our directory is to understand the subatomic world deeper and deeper, and to uncover ultimate laws of nature. We are exploring some of the most compelling mysteries in contemporary physics. These include the essence of dark matter and dark energy, the possibility of hidden symmetries of nature, and the mechanism that break them, and the fundamental nature of the vacuum that ultimately drove the evolution of the early universe. The visible world surrounding us is made of molecules and atoms, which in turn consist of protons, neutrons, and electrons. You may have learned in school that neutrons and protons are the building blocks of atomic nuclei. But did you know that these particles consist of even smaller particles called quarks and gluons? These elementary particles interact through the strong force, one of nature's four fundamental forces. The general theory that describes all elementary particles which do not have internal structures, such as electrons and photons, are called elementary particles. And as well as their interactions, except gravity, is known as the standard model of particle physics. Scientists at Brookhaven contributed enormously to the development and completion of the standard model, including the Nobel Prize-winning experiments conducted at Brookhaven's alternating gradient Synchrotron AGS machine. Over the past nearly 30 years, discoveries of new particles, such as the pop quark, the tau neutrino, and the Higgs boson, have impressively confirmed the validity of the standard model. However, many unsolved questions remain. For example, the nearly perfect symmetry between matter and antimatter in the standard model implies neither should have survived a second after the Big Bang. Yet, we live in a universe that is dominated by matter. The standard model also cannot explain scientists' observation of dark matter and dark energy. Physicists at Brookhaven are actively looking for new physics beyond the standard model. One place to look for new physics is precisely measure the muon magnetic moment. The muon is a big sister of the electron. It is just like the electron, except it is about 200 times more massive. Such an experiment carried out at Brookhaven in the late 1990s and early 2000s, called the muon G-2 experiment, showed tantalizing evidence for new physics. And the result has recently been confirmed and announced by a follow-up experiment at Fermilab in spring 2021. While the discovery of the Higgs particle explained why elementary particles have mass, it does not explain the mass of the proton, neutron, or other composite particles. Where the proton's mass comes from is one of the many important questions that will be answered by experiments at the future Electron Ion Collider that will be built at Brookhaven in the next decade. The Electron Ion Collider will be a particle accelerator that collides polarized electrons with polarized protons and atomic nuclei. to produce snapshots of those particles' internal structure, like a CT scanner for atoms. Brookhaven's existing particle collider, RIC, is the only hadron collider in the US and only polarized proton-proton collider in the world. At RIC, scientists recreate the conditions of the early universe by freeing quarks and gluons from confinement and creating quark-gluon plasma, which is believed to have existed about a microsecond after the Big Bang. RIC scientists also discovered that quark-gluon plasma is a perfect liquid. Now, let me come back to the S-Phoenix experiment at RIC, which is where I'm sitting today. S-Phoenix will provide state-of-the-art capabilities to study quark-gluon plasma on different length scales and answer the question, where and how does plasma transition from quasi-particles to structureless, perfect fluid? The goal of S-Phoenix is to understand the microscopic structure of the plasma and review how its strongly interacting nature arises from the underlying interactions of quarks and gluons. At Brookhaven, we develop unique technologies to carry out our science mission and for applications of societal benefits. For example, the injectors at the RIC accelerator complex are used for application programs such as the production of medical isotopes and space radiation studies to protect astronauts. In 2025, after we complete the RIC science mission, RIC will be converted to be the hadron ring of the Electron Ion Collider. The Electron Ion Collider will advance our knowledge about the structure of the visible matter in the universe, maintain the US leadership in nuclear physics, and allows for the STEM workforce development and the development of technologies of societal benefits. We have an exciting future ahead of us. Thank you.
Thank you, Haiyan. I love a good unsolved mystery, and it's fun to find out there's quite a few in the nuclear and particle physics fields. Now, I'd like to turn it over to John Hill, Director of the National Synchrotron Light Source 2. John, please tell us a little more about nsls-ii and the range of research that takes place there.
Thank you, Cahill. It's a great pleasure to be here with everyone tonight, and thank you for the chance to talk to you about what we do here. I thought I'd start by explaining what a synchrotron is. These are accelerators. They accelerate electrons around in a ring, and they're originally built for particle physics, like Haiyan was just talking about, to understand the properties of the electrons. But what was realized was that the electrons go around the ring, they produce X-rays, and various scientists figured out those X-rays would be useful to use to do other experiments. So these were material scientists who would come to these facilities and hang on the edge of the particle physics experiments and try and do some material science sort of in the background. They were called parasites on these other machines. So when these was first started, they realized these were really powerful experiments, really useful. And so Brookhaven was the first lab to build a machine just to produce the X-rays. Forget the rest of it. In materials, and that helped things like hard drives in your computer systems. They also were able to look at surfaces for the first time using X-rays, and that was really important for understanding some semiconductors and catalysts. And just generally new ways to image objects with X-rays came out of the original NSLS. Perhaps one of its biggest impacts was in the field of biology, where biologists realized they could use these X-rays to solve crystal structures of proteins, and that gives you information about the atomic structure of those proteins. And that's really important for things like drug discovery, trying to understand how these proteins function inside plants and animals. Thousands of protein structures were solved at the old NSLS. One particularly famous example was solving the structure of a protein channel or ion channel inside a cell membrane that allows the potassium to go inside that cell. That's really important in terms of things like how your heart functions or how neurons function inside your brain. And that work won the Nobel Prize, work that was done here at Brookhaven. So I'll just note, by the way, just a personal point, I still remember very clearly my first ever experiment at NSLS as a young graduate student coming down to do an experiment there. I've been doing experiments back in my home lab at MIT using a lab X-ray source. And when I came to NSLS, the beams were so intense, it was just this fabulous experience. Now experiments that took me hours or days back home were taking a few seconds. So it was just this real rush of data coming in. It was really a wonderful experience. And that was one of the reasons I came to Brookhaven, was at the time we had the best synchrotron in the world. And that's why I wanted to be here and use that machine for my research. As I said, NSLS ran for 30 years. And of course, over that time, other people built synchrotrons here in the US and around the world that were bigger and brighter than the NSLS. And it came time to replace NSLS and build a new machine. And that is what nsls-ii is. That's the new synchrotron here at Brookhaven. It's bigger, better, and brighter than the old NSLS. I'm hoping right now on your screen, you're seeing an aerial view of the two. And the NSLS, the original machine, is up there on the top left-hand corner. You can see it's much bigger. It's big enough to fit Yankee Stadium inside that ring, so it's about 1 kilometer in circumference. We are 10,000 times brighter than the old NSLS was. So that's, again, a huge gain in what you can do experimentally. It took about $1 billion to build the machine and the first few beamlines, and about 10 years to construct from the start of the design phase till when we turned it on. So it's a really big step forward. It's a bigger jump from the old NSLS to the new nsls-ii as it was from my old lab machine to old NSLS. So you can see this kind of these big, huge jumps we're taking as these new machines turn on. So nsls-ii turned on 7 years ago now. We have 28 beamlines built here. A beamline is the piece of equipment that takes the X-rays from the ring out to your experiment. So that means we can carry out 28 different experiments simultaneously here. And we supply X-rays or light from all wavelengths, from the far infrared all the way up to the hard X-ray. And each of these 28 beamlines is optimized to do something different. So some might be imaging the atomic structure or the chemical structure or the morphology of your material. What we do really well here is do that with very high precision, very high resolution, very high sensitivity, because we have these such intense beams of X-rays. And people have been studying all kinds of things here at nsls-ii, from batteries to plants to catalysts to the latest generation of microelectronics. It's a really very wide range of research that gets done here. We have at least 2 world record holders here. We have a beamline that has the smallest X-ray spot in the world in a microscope. It's 10 nanometers across. And just to translate that, 10 nanometers is 30 gold atoms. So really very tiny beam. And we can use that for looking at processes down almost the atomic level, let's say in a battery. The other record holder we have is in energy resolution. That means we can measure the energy of those X-rays with much better precision than you can anywhere else in the world. That's in fact the beamline I'm sitting at in front of right here in the background here. It measures the energy of the X-ray going in and going out and looks at the small differences in those energies after the X-ray bounces off your sample. So over my left-hand shoulder here is where the X-rays come from, behind that white wall. They pass down the pipe and they hit a sample which is contained in the chamber of my right-hand shoulder, bounce off that sample, and then go down into the detector along this arm that's labeled SIX here. And we do that, as I said, with really high precision. Why would you want to do that? That tells you how the electrons are moving inside the material with really high precision. Again, better than you can do anywhere else in the world. And so people come from all over the world to use this instrument because it's such a great instrument. So we turned on, as I said, 7 years ago. We've done some amazing things in that time with the beamlines we've got built right now. Our biology beamlines, for example, can look at some of the smallest crystals around, and we've been solving crystal structures. We're solving protein structures with atomic resolution for drug discovery, for understanding the processes in human health and in animal health. We've looked at lithium-ion batteries and how they charge and discharge, and watched the little tiny electrode particles that are a few microns across break apart as the cell of the battery fails, and try to understand that process. And we've looked at the latest generation of microelectronics from IBM, where the transistors are a few nanometers across. Being able to study that at these beamlines and look at those very thin, small silicon structures to understand how we can make better silicon chips in the future. There's been a wonderful time already here. We've got many, many years of successful operations ahead of us. But if I start to look ahead and ask what we want to do next, well, as I mentioned, we have 28 beamlines here. In fact, that's about half as many as we could have. We could have up to 60 beamlines. So we'd like to finish building out the facility. adding new capabilities that we don't have today to be able to do new science on those beamlines. We like to build out our data infrastructure. These beamlines are producing huge amounts of data, very high data rates, very high data volumes. We want to be able to handle that using the latest AI and ML, artificial intelligence and machine learning techniques to basically build self-driving experiments, autonomous experiments that can help the scientists take data really efficiently and really quickly. And then looking yet further ahead into the future, we've been thinking about what the next machine would look like. I mentioned NSLS, now we've got to NSS-II, what's after that? And we've already got designs on the books that would give us another factor of 100 increase in brightness on where we are today for that next big generation jump into the future. So that's maybe 10 years out, something like that, but a really exciting thing to imagine going forward. So really exciting facility here. As I said, it's still very new. We're still doing wonderful things, but we're really looking forward to the future here. Thanks,
Thank
Neil.
you. Thank you, John. Sounds like a fascinating and multidimensional research facility for sure. And now we'll hear from Allison McComaskey, Chair of Brookhaven's Environmental and Climate Sciences Department. Allison, if you would, please tell us more about environmental and climate sciences at Brookhaven Lab.
Yeah, sure. Thanks, Cahill, and thanks to all of you out there for joining me and the Environmental and Climate Sciences Department to celebrate the lab's 75th anniversary. So obviously, Brookhaven is very well known for its great physics research, and we just heard a little bit about that, but climate science has also been a big part of the lab's portfolio for several decades. Our researchers here, they spend most of their time doing fundamental research that advances our basic understanding of the climate and also impacts that humans have on the climate. But we also use this knowledge to help develop technologies for a clean energy future and to develop solutions to the challenges that climate change brings. Our particular strength here at BNL is in climate observations. So we have world experts in radar science, in observing plant physiology, in measuring the properties of air pollution. And we have a really long legacy of innovating new measurement approaches and instrumentation. We match this observational expertise with building a theoretical understanding of the fundamental building blocks or the very small elements of climate. So it's kind of similar to the quarks and gluons that Haiyan just told us about. But for the climate, those fundamental building blocks are aerosol particles, cloud droplets, and characteristics of plants that cover the Earth's land surfaces. So right now I'm standing in one of our several aerosol labs, and behind me is a small subset of the many aerosol instruments that we used both in the lab and the field. So aerosols are tiny particles suspended in the air, and many of us think of that as air pollution, but they can also be natural in origin, like dust or from sea salt, or even the volcanic eruption like the one in the Pacific a couple of weeks ago. So aerosols are important to climate because they can block incoming energy from the sun. That blocks the energy from reaching the Earth's surface, and so they can act to cool the planet and mitigate warming caused by increases in greenhouse gases. On the other hand, in the case of soot or carbon that's produced from fuel burning, aerosols can be very dark and they can absorb solar energy and actually heat the atmosphere. So it's a complex thing, and we need to understand a lot about aerosol properties to understand how they impact the climate. In addition to that, aerosols serve as seeds for cloud droplets. So water condenses onto these tiny airborne particles, and cloud droplets and clouds are another one of the fundamental building blocks of the climate that we study. So we use these instruments to measure many different properties of aerosols, including their size, their chemistry, how they interact with the solar energy in the atmosphere. We also use a similarly wide range of instruments in both the lab and the field to study plants and their role in mitigating climate change as well. About a third of our annual carbon dioxide emissions are taken up and stored by plants. And this storage, it actually subsidizes our use of fossil fuels by removing large quantities of carbon dioxide from the atmosphere. But the subsidy in the future of how it will evolve is very uncertain. So we use these measurements to investigate the capacity of plants to take up carbon dioxide and to better understand the role that plants will play as climate change evolves into the future. So a little bit of a visual on some of our field measurements and our field deployments. We are part of DOE's atmospheric radiation measurement user facility known as ARM. ARM's been around for almost 30 years now, and it operates these very large atmospheric supersites in the US and around the world. I think what you're seeing is a visual of these. The observatory at the top is in the Azores, and this site was designed to study marine boundary layer clouds. These clouds are especially sensitive to climate change, and they constitute a large uncertainty in climate models. At the bottom is our facility on the North Slope of Alaska. So this observatory provides us with better understanding of the massive changes that are happening in the Arctic right now, like we see in this very dramatic loss of sea ice cover that's been happening over the past several years. So we're also part of DOE's Next Generation Ecosystem Experiments, or what we call NGs. To the right there is my colleague, Alistair Rogers. He's on the Alaskan tundra for an NG Arctic experiment with mosquitoes. So I know those might look like birds on your screen, but they are actually bugs, and they can present a pretty challenging work environment. So like I said, Brookhaven's been working in basic or fundamental climate research for decades. But more recently, we've been leveraging that expertise to understand the best ways to mitigate the impacts of climate change and also the best ways to implement clean energy. This is especially important in cities just by the fact that they're large population centers. They have a lot of infrastructure, and this infrastructure can both exacerbate and be vulnerable to extreme climate conditions. So a few months ago, we set up an ARM deployment in Houston, which is the first of its kind in an urban area. And we squeezed it into Houston, but it's really not possible to get these very large field deployments into the center of a city like New York or Washington, DC, that's very dense. But these are areas where there are a lot of people, and we want to be able to assess climate solutions down to the building scale in these areas. So another visual of some field deployments. Here at Brookhaven, we've used our expertise to develop advanced measurement and modeling solutions specifically for urban science. What you're seeing here is a highly instrumented mobile facility that we call the truck. And we've taken it through the heart of New York City, like you see here, to collect data that can be used to study problems like the urban heat island or air pollution. And, you know, investments are being made by DOE right now to implement clean energy options and to make sure that the benefits of those investments are distributed equitably. This facility helps us help DOE do that. So if we want to build solutions that address issues down to the neighborhood scale, we need to be able to measure and make predictions at those same scales. With this new observatory, we can drive this truck from neighborhood to neighborhood and measure the differences between, say, high income and low income areas and how climate affects them differentially. Or we can assess the energy efficiency of particular buildings. We pair these with our new ultra high resolution models that we're developing. And so we can also assess whether these solutions that we implement are working or not. An example of that would be if we plant more trees in the city in a low income neighborhood, which tends to have less vegetation to cool the neighborhoods, we can then go back and measure any difference it made. And then we can use that information to model the longer term impacts of that solution. So there's a lot to our BNL climate story here, but I know you have a lot of questions of your own. So Kahil, I think I'll pass it to you to take those.
Well, thank you, Allison. I know climate science is a topic of interest to many. And thank you, Haiyan and John, for your remarks as well. We do have a few questions from our viewing audience, so let's get into it. The first one we'll start with is actually a question from Randy via email, who asks, are there any plans to use Brookhaven's Northeast Solar Energy Research Center for green energy research? And I think this might be something that you could speak to, Allison.
Yeah, definitely. So for those of you that aren't aware, here on Brookhaven's campus is the Long Island Solar Farm. And this is the largest solar farm in the eastern US. And this NERSC facility is part of that. And it's kind of like the research arm of the Long Island Solar Farm. And it's a great thing for us because we have all of our instrumentation here to measure atmospheric properties. We can pair that with this facility that provides measurements on solar power production. And when we use the two together, then we can really understand how weather and climate affect solar productivity and solar efficiency. And we can use that to create technologies, either different materials for solar panels or even software that operates these solar facilities to make them more efficient as the climate changes.
Great, thank you. So we have another question. This one is for John, and it comes from Phil on YouTube, who asks, are there any needs for instrumentation R&D, which I believe stands for research and development, at nsls-ii?
Yes, huge. So, we produce these very tiny beams of X-rays, but then you need to use them somehow. So that means, for example, you need to move your sample in with that really very high precision. You need to move it around in the beam to very high precision. Maybe you need to move a detector around that. We have huge instrumentation needs for sample manipulation. So we work very closely with engineers, both in-house and externally, to build the instruments. The kind of instruments you see behind me here, for example, typically designed in-house, but then we have them manufactured externally and then bring them in. So instrumentation covers a whole range of things, from detectors to optics to the nano positioners, and we use all of those here all the time.
Well, it sounds like lots of different kinds of people could potentially be working at the National Synchrotron Light Source too, in lots of different ways. And for you joining us, watching the live stream, please keep those questions coming. I'd love to see them coming through. We have another one for Allison, actually from a YouTube viewer, who asks, you mentioned a field study, and where are those experiments taking place? I did recall you mentioned something about Houston, but then also Alaska. Are there lots of field experiments taking place in different parts?
Yeah, we have experiments taking place all around the world. So these couple of facilities that I mentioned that DOE runs, the first is the atmospheric facility. It has 6 different observatories. There are 3 fixed sites. You saw 2 of them. One is in the Azores, one is in the Arctic, and there's also their original flagship facility in the Southern Great Plains of the United States. So it's out there in Oklahoma. But then we have 3 mobile observatories, and they get deployed everywhere around the world you can imagine. And they're deployed maybe for, a year or so at a time. The next generation ecosystem experiments, there is the one in Arctic that you saw, but there's also one in the tropics. And so we have some of our researchers down in Panama taking part in that right now. So we love to go anywhere and everywhere in the world to sample all those different climate regimes.
Yes, and it sounds like it would be really important to develop accurate models to get information from all over the planet.
Exactly.
Well, we have now another question. This one is for Haiyan, actually. Haiyan, the question from viewer is, will the Electron Ion Collider really produce 3-dimensional images of a proton? Oh, we can't hear you just yet.
Yes. So, actually the inside of the proton is a very, very complicated landscape. It's dynamic, and very complex. And the kind of experiment we will be able to do with Electron Ion Collider will allow us to look at the three-dimensional structure in multiple ways. For example, we will be looking at that in three-dimensional so-called momentum space. And we will also be able to look at that in terms of a hybrid. One dimension is momentum, the other is the transverse space. So the kind of experiment we will do involving different kind of processes. And some of the processes are called exclusive processes, means that we will be detecting all the particles coming out in the final state. And other experiments involved, we will detect not completely, but we will detect a combination of particles coming out. So in the end, when we do all these kind of measurements and analyze the data, which we will benefit from, algorithm, from machine learning and AI. And in the end, we will be able to, essentially, we can make movies of what's going on inside the proton in this kind of three-dimensional way. And then we can also compare with what the fundamental theory of strong interaction, which is called quantum chromodynamics, and that can predict the kind of behavior. And then we can also compare with the theory. So it's actually very exciting, but it is also very complicated. So it takes a lot of work and takes, Electron Ion Collider as well as state-of-art detectors we will be building for EIC.
Definitely, I can imagine that is quite complex, but also very exciting. All right, keep those questions coming. Thank you. We've got some question here. This one is this actually is about the National Synchrotron Light Source 2. So I think John will probably take this one. The question is, how does an nsls-ii X-ray compare to an X-ray that someone would get at a doctor's office, for example?
Okay, good question. So the X-rays at the doctor's office are what we call high energy X-rays. We measure them in kilovolts, doesn't matter, but let's say 80 kilovolts. They're very penetrating. They go straight through your teeth in that case, and they produce a shadow that you can see where your teeth sit. The X-rays we use here, very similar, but different energies, which means different wavelengths, and so they have different properties. So they might not be as penetrating, but they might bounce off the atoms we're interested in looking at. So maybe we're interested in looking at, I don't know, copper. So we're going to choose an X-ray energy that will look very cleanly at the copper. So we'll tune the energy so just to pick out the copper atoms. So they tend to be lower energy than the X-ray from a dentist's office. That's the X-ray itself. Then the other big difference is there are many, many, many more of them here than you would ever get at your dentist's office. So we have to take safety very carefully, of course, so everything is shielded and locked away when the X-rays are on. But they're very bright, very intense beams of X-rays. So I don't know quite how to compare them, but the difference might be, I can't think of numbers to quantify it, but hugely more bright here than you would ever get at a dentist's office.
Okay, great, sounds good. I have a question here for Allison, actually. And it's a good one because I've never heard of this thing before. This question is from Anthony on YouTube, who asks, what are your thoughts on atmospheric rivers and the data that you'll be able to compile on them? And what is an atmospheric river?
Yeah, so that's a great question. Atmospheric rivers, and I'm an aerosol scientist and I'm not a meteorologist, so I'm not going to be great at answering this question. But atmospheric rivers are something that have gotten a lot of attention recently, and they're kind of what they sound like. So they are, large areas of flow in the atmosphere that cover, we get atmospheric rivers that travel from the equator around the area of Hawaii to the coast of California and bring a lot of moisture with it. And sometimes this is why we get big snows in California and the like. But our scientists are starting to understand how atmospheric rivers work and how they happen in different parts of the world and how they can contribute to really extreme weather in different areas. And the behavior of atmospheric rivers is changing a bit as the whole global climate changes a bit, that larger environment. So while we don't necessarily study atmospheric rivers specifically here at Brookhaven, the kind of work that we do, the detailed understanding of how clouds behave in different meteorological conditions contributes to that understanding. And it is something really important for us to learn more about it in the future because of that extreme weather and those disturbances that they cause.
Oh, thank you. Thank you. I learned something new today. I'm actually learning a lot today, so thank you all. This next question from Chris on Facebook is one I think probably you all have something to say about. It's asking if we can talk about the role that quantum computing plays in your research. Haiyan,
okay.
John? Yes.
I was going to start, which is we don't yet have a quantum computer that we're using in day-to-day work here, so we can we're not using them yet, I would say is the short answer to that. Not seriously anyway, but we're just beginning to get to the point where we might be able to use them to calculate some properties in what we call condensed matter. So solid state systems quantum computers might be able to calculate those kind of things faster than the conventional computer. The other place which probably Haiyan will talk to is in terms of high energy physics and calculating collisions. So those are places where quantum computers might begin to play a role, but we don't yet have a working quantum computer that can be used in everyday real life calculations. They're more little tiny test facilities at this point. What I will mention is that at nsls-ii, we're doing research to try and improve those quantum computers, make them bigger meaning able to handle larger calculations, faster, more stable. That comes down to materials you make these computers out of. And so we can do a lot of that materials research. In fact, even the beamline I'm sitting at right now has done some work trying to get better, what we call qubits, which are the sort of fundamental building blocks of a quantum computer, so that maybe in 5-10 years time, we do have those big quantum computers that can really do real calculations that would help us.
Yeah, so what I like to add is that, some of the calculations physicists, would like to calculate right now is limited by the classical computer in terms of, it's just not scalable in terms of the amount of computing power you will need. And they are, scientists, physicists working on that to compare the calculation done on quantum computer versus a classical computer. So this is actually one area, but also I actually just recently learned, I still need to learn more, but it's actually quite fascinating. Some of the colleagues here in the Collider department proposed the idea to use accelerator, as a quantum computer as well. So which is actually fascinating. So I think that we have seen major progress in quantum computing, and it's becoming real, helpful to many areas in science.
Thank you. Right, we've got lots of questions coming in, so let me pick one of these next ones. Question is for Allison. This is from Denise on YouTube. The question is, has Brookhaven's unique location, especially its proximity to the Pine Barrens, provided benefits to the climate research?
Yeah, so we do some research locally. Our terrestrial ecosystem science and technology group has done some research in the Pine Barrens here. They've looked at how fires and ecosystem succession, how the ecosystem grows back after fires progresses. Other than that, it's a very nice environment to work in.
I agree. All right, our next question for Haiyan. What is the difference now between the Electron Ion Collider and Brookhaven Lab's current particle collider, the relativistic heavy ion collider? And then what about the large hadron collider in Europe, and how does that kind of compare? How do they compare?
Yeah, so the Electron Ion Collider, so one beam is electron, which in physics language we call leptons. And so the electron is a fundamental elementary particle, as I mentioned earlier. It means that it doesn't have internal structure. It's like You can think about that as a point-like particle, right? And so in this case, it's electron ion collide, right? So currently, RIC, which is heavy ion collider, and we can collide proton on proton. We can also collide, gold on gold, and other ions. Means that those are composite particles. And Large Hadron Collider is a higher and much higher energy version of the RIC, if you want to think that way. And so at RIC, we're talking about center mass energy per particle pair is a few hundred GeV, and at LHC, so you are talking about TeV, right? A few TeV per particle pair for the collision. And so for PP, it's 13 point some TeV. So 1 TeV is 10 to the third, GeV. So it's just much higher energy. Thank you.
Okay, thank you. Our next question is for John. What types of beamlines will be added to the National Synchrotron Light Source 2 in the future?
Okay, great question. As I mentioned, we're about half built out now, so we have space on the floor for additional beamlines. The kind of things we want to add are beamlines, well, two types of beamlines. One, types that we don't have currently, so adding capabilities we don't have right now. So that might give us new energies of X-rays that we can't access easily now. So building a new beamline to do spectroscopy at one energy that we can't cover right now. So that would complement the stuff we've got already. The other thing we want to do is we've got 28 beamlines, but they're all oversubscribed. But if many more people want to come and use them, we can use them. So adding more capacity will be really helpful. And then we would do it in a very highly automated way so that people can remotely use them. So these new beamlines would add capacity, throughput to allow us to service more users. I didn't mention this at the start, but I should have done. We're a user facility. We're here for people to come do their research here to help them get their research done. So we want people to come here, carry out their research and make that successful. So if we have more capacity, then we can push, get more experiments done and have more users come through. So adding capabilities that we don't have now, and then adding capacity that to complement what we've got already.
Okay, thank you. Our next question for Allison, from Anthony on YouTube. Do you include solar forcing in your climate models?
Yes, we do. That's so solar forcing now. That's closer to what I do. And so just a little bit of background. There's two ways that we can talk about how climate change is affected. And one is a forcing, and that means that there's something from the outside of the system that exerts a forcing on the system. And so we define those as things like greenhouse gases or aerosols. And because they're human-made, they're what we call anthropogenic, they're from outside the system. Now, clouds are a huge element in climate change. One of the biggest uncertainties that we have, and their behavior under changes in climate is complex and it's uncertain, but because of their part of the natural climate system, we call it a feedback. So forcings exert an initial forcing on the system to change it, and things like clouds represent a feedback to that initial forcing. Their change is a feedback. So aerosols and clouds represent two of the large solar forcings of the climate and change in temperature. And that's really what we work to do. We work to understand how aerosols and clouds affect the solar radiation as it moves through the Earth's atmosphere and hits the surface and warms the surface, which then again provides the energy to develop clouds and those things. So yeah, it's right on what we do.
Thank you, thank you. Our next question is for Haiyan from Paul on Facebook, who would like to know if you could tell us more about the detector behind you. Who's putting it together and when will it be ready?
Oh, wow, that's a very good question. So this is the, you see the S-Phoenix as it is currently. It's not done yet, but you can see that on the aluminum-looking big can is a superconducting magnet. And what you see outside the blue array are the outer calorimeters. And right now we have 20 mounted. And we will continue to mount the other sectors, and then inner calorimeter, as well as electromagnetic calorimeter, and time projection chamber, and they will be installed in the near future. And so our plan is that we will finish the construction installation this year, and then next year, FY fiscal 23, we will start to commission the detector with beam. So it's actually very exciting, and well, thank you very much for the questions. I get the chance to show you.
Yes, I was going to say that is exciting because it's a new detector, and hopefully, and it looks beautiful actually. So
it's not a Zoom background, and I tried to figure out a way to show you it's real. Okay, I'm really in front of this detector. I'm very excited.
It looks great. It looks great. All right, great. Keep those questions coming. Thank you, viewers. We have another question. This one is for John about the research, NSLS-2's research on quantum materials. So you mentioned that some of NSLS-2's research is focused on quantum materials. What other kinds of research are happening at your facility right now?
You mean other kinds of quantum material research, or just research in general?
Maybe both.
Both. I'll talk about quantum materials first, and I'll broaden it a little bit. The kind of things that, in general, what we call quantum material is a material which is properties are determined by quantum mechanics in some unusual way. And so there are things like superconductors that behave, superconductors material that carries electricity with no resistance. And that's a quantum effect. So we're interested to understand those quantum properties of materials. And that in general comes down to understanding how the electrons are moving inside those materials. And so we can do that with X-rays in many different ways. We can bounce the X-rays off that electron, and then it tells us about how the electron's moving, or we can kick an electron out and look at the electron coming out. So that gives us information about the electrons moving, and then we try and extrapolate the quantum properties from that. And then, as I said, one application of that might be to build a quantum computer down the line, but other applications might be to build a better conventional computer, but using maybe magnetism instead of charge, something like that. So that's the quantum materials. But that's by no means all we do here. We do a whole range of research. So we've got a lot of people very interested in batteries, building a better battery. The battery in a cell phone dies after a few years. Why? What's going on there is a complicated process by you charge and discharge your battery. That's moving atoms in and out of electrodes. They swell, they shrink, and eventually they crack and fall apart. So we can look at that in great detail here. We can look at the chemistry going on there, how they fall apart, and then try and design materials that wouldn't fall apart or would stay together longer. So again, that's all about using the X-rays to look at the battery while it's charging, discharging. So we bring the X-rays through some cases, the steel canister of the battery itself, watching it in great detail. So that's the kind of thing we can do. Energy storage. I can keep talking for as long as you like, Kale, so you have to stop me.
I imagine that there's lots of different kinds of research there, but you're mentioning like energy materials, like batteries, and
batteries,
you didn't.
Catalysts we look at microelectronics, we've looked at plant cells, from people from Allison's department, whole range of sciences.
Yes, I was wondering about the biological sciences. You look at plant cells and maybe other kinds of, you were mentioning before proteins and those kinds of things that are related to biological studies. So it sounds like the NSLS-2's got a wide range covered.
We do, and yeah.
Great. Okay, let's see. We've got another question, this one for Allison, actually. This is about, it's asking, how does data science contribute to our knowledge about climate?
Yeah, that's a great question. And more and more. So the climate system is very complex. And so we have to be pretty clever in how we build instruments and field experiments and go out there to measure things to tell us what's going on. Between the kind of work that we do here, where we go out and do field deployments, and also the information that we get from satellites. Satellites are taking images of the planet all the time. We also fly aircraft through the atmosphere, and we use those to take images of the Earth. So there's a lot of different data out there from a lot of different sources. And it can be just as complex to figure out how to put all that data together to tell a coherent story, to tell us what it is that we need to know to fill that knowledge gap that we have to build a better prediction and a climate model. And so we are looking more and more to data science to help us do this, to take advantage of the huge amounts of data that we're taking, but also the huge amounts of data that exist from the past, and bring it all together. Another aspect of that is, until now, our climate models have mostly been physical representations of the climate. But we're finding that we can sometimes get better predictions if we build a data-driven model. So we take those data and we use machine learning and artificial intelligence to build a predictive model using the observations themselves. So we are very actively working with our computational sciences initiative here to build those applications.
Yeah, well, definitely sounds like data science contributes quite a lot to our knowledge about climate. All right, this next question is back to the S-Phoenix detector, which I think is fascinating. How will this newly upgraded S-Phoenix detector improve upon the original Phoenix experiment?
Oh, yeah, that's a very good question. So there are a few things. As you know, for this detector, what we really wanted is really to understand the detail in terms of how, the quark-gluon plasma from, the kind of quasi-particle transition to perfect liquid, right? So in order to do that, so this new instrumentation has a number of improvements compared with the previous Phoenix detector. One is that it is able to really take the advantage of the RIC luminosity, which is 50 times more compared with the original design luminosity. So therefore, it is able to take data at a much faster rate. And so that's one, very important. And the other is also the precision. And because we want to use variable kind of probe, so we can look at the detail of this plasma, right? So that's why we have a superconducting magnet. So the magnetic field is actually 3 times compared with the other detector, for example, STAR. So magnetic field is very strong. And also we will have a state-of-art tracking so that we can, track the particle very well. And also capabilities in terms of measuring the energy of the particle well. So we have parameters outside of the magnet. So these are the kind of major improvement which will allow us to accomplish the scientific goal for S-Phoenix.
Thank you. Right. This question is from Peter on YouTube, who asks, is Brookhaven doing any research on COVID-19?
I'll take that one. The answer is yes, we're doing a lot. Let's see where to start. So I'll start with nsls-ii. We've done a lot of work there. So COVID-19, obviously a virus. The virus is made of proteins. It's a ball typically with proteins around the outside. Those are called spike proteins. They bind to cells inside your body. They take the proteins that are inside the ball, they put them inside your cell, and they take over your cell and make a whole bunch of other viruses. So that's how you get infected. So we've been trying to understand that mechanism, looking at the proteins inside that ball, trying to understand exactly what atomic structure they have, and then binding them with potential drugs that might come in and stop that process happening, stop you getting infected or stop it being a really bad infection. So we've had a number of, I think, 40 or so structures we've solved here of the proteins within COVID-19, bound with various drugs. Some of those drugs are now working their way through the clinical trials. Maybe there'll be something that can get used in the future. We had Pfizer here, by the way, looking at their vaccine in the early days, so we're very proud of that. More generally at the lab is using other techniques to look at ways to help fight COVID-19. So we've had people modeling the way the virus aerosols, Allison's area, how the virus particles might flow through a building, right? And how you might trap them or at least model them and understand that. So how effective is a masking? So that kind of research. And we have some people working on new ways to detect COVID-19 to build better tests that you might eventually have in your house, just like a little, maybe it's attached to your phone that you can breathe into and figure out if you've got COVID-19 and early detection. So a whole range of research going on here to try and combat COVID-19.
Wow, thank you. Thank you very much for that. Excuse
Can I add
me.
one piece that I forgot to mention?
Please, please.
A big piece of drug discovery is trying to figure out which drug binds with which protein. And there are many literally billions of combinations of drugs and protein, what they call pockets. And so one way to speed that search up is to use computers and have them simulate the binding ahead of time. So we have a strong computational effort that's modeling this. They hand their results to experimentals to see if it works. And then there's kind of this feedback loop to try and speed up drug discovery. And that's been really powerful here at Brookhaven.
Thank you. Okay, question for Allison from Joe on YouTube, who asks, how much does atmospheric pollution contribute to worldwide temperatures? If the US stopped all atmospheric pollution, how much would the temperature change?
Yes, well, if we stopped all atmospheric pollution, it might change a noticeable amount. So I will say that, about 20 years ago or so, we implemented some clean air policies, maybe starting 30 years and a few after that. And our measurements definitely show the decrease in atmospheric aerosols due to this clean air policy. And we've been able to calculate, how that affects the energy that reaches the Earth's surface and how that might affect warming. The interesting synergy between air quality and climate is that aerosols tend to cool the Earth. So when you take them away, you stop that mitigation of the warming that they provided. And so we're kind of at counter purposes here. We definitely don't want to warm the climate anymore, but we also want to reduce air pollution. So it's an important area of study. And I think, as you can imagine, in some regions of the world which have, much worse air pollution issues than we do here in the US, understanding how that is going to affect the climate as those nations evolve and change their energy structures it's very important to the climate.
Thank you. Thank you. Our next question is from a YouTube viewer, and it asks, the question is Brookhaven doing any research on clean and safe nuclear power? I don't know if anyone knows whether or not we're doing any research on clean and safe nuclear power.
Certainly doing some research here on new materials that might be used for reactor vessel steels, for new fuel rods, things like that. So the kind of material science behind building a new reactor with a new kind of technology. As far as I know, we're not doing work on the reactors themselves directly.
Okay, so material science related to,
for example, as a reactor vessel steel containment vessel that keeps everything safe, but as that gets irradiated, the steel ages and eventually becomes brittle. So studying that process and trying to understand how it becomes brittle and predicting that is really important in understanding the lifetime of a reactor. So that's the kind of thing that we do here.
I see. Great. Thank you. So our next question is for Haiyan. And I wondered about this too. What will happen to RIC when the Electron Ion Collider is being built?
Okay, so as I mentioned earlier, currently we're running the RIC program until 2025, and then we will actually work on converting the RIC ring to become Electron Ion Collider Hadron ring, and so this is basically we are going to use the RIC accelerator complex to be part of the Electron Ion Collider. And our injector will contribute to that for light source, and certainly a lot of work will happen for the conversion. And so in the end, when we finish everything, we will have the Electron Ion Collider. The original RIC ring will be part of the Electron Ion Collider.
Hey, great.
Hill, can I add one more answer? sorry,
Yes.
to go back to the nuclear energy question, one of the new reactor technologies is using what's called molten salt, which is a liquid fuel. And we're doing a lot of research on understanding how they, the properties of those molten salts and how you can contain them safely. So that research is going on here.
Molten salts.
So a salt, like table salt, sodium chloride, if you warm it up high enough temperature, it melts and becomes a liquid. So these would be salts like that could transfer the heat out of the reactor and then use it to drive, generate electricity that way.
Okay, so this would be a cleaner type of safer nuclear.
Exactly.
Okay,
right.
All right. Thank you. Thank you for that. All right, Allison, question for you. And I think you did touch on this a little bit. Maybe you can tell us a little bit more, but why is studying clouds so important?
So clouds are really important to the Earth's climate because they're bright and they're ubiquitous. So, clouds are everywhere, almost all of the time. And they increase the reflectivity of the Earth quite a lot. If you think about how dark an ocean surface is, and 70% of our planet is covered by the ocean surface, if you have sunlight coming in and it hits the ocean surface, it's dark. It's like wearing a black t-shirt, it's going to absorb that energy and make it warmer. If you put a cloud over that ocean surface, you change the reflectivity dramatically, from one end to the other. And a lot of that energy is going to be reflected back out to space. So the amount of clouds, the thickness of clouds, it's really important to know that, to understand how much energy gets reflected out to space rather than absorbed into the Earth's system. And now clouds are also very sensitive to changes in vertical structures of temperature and humidity within the atmosphere. And so what we try to understand is how clouds are going to change in response to those temperature and humidity changes in the atmosphere, and thus, like I was saying before, feedback on climate change.
That's so cool. Thank you. One of my favorite things to do is look at clouds, and who knew they were so important to climate? Okay, our next question, and keep those questions coming. Thank you for these incredible questions that you're asking. I'm so happy that we're able to get to most of them here. This question is for John from Wade on YouTube, who asks, do we have plans for an nsls-ii?
Yes, we have ideas for what it would look like. Let's put it that way. Don't have concrete plans yet, but the way we generate the X-rays, as I said, we accelerate the electrons around in the ring, and generating very bright X-rays, meaning packing those electrons into really small bunches and keeping them very tight, and lots of them. And so we've been looking at ways to do better than this machine here by maybe 100 times more X-rays coming out of it. We call it nsls-ii right now for upgraded nsls-ii. But these are ideas on paper that we're testing out now to see if they work, and then hopefully get funding to build out the machine that way.
All right, so we have something to look forward to, an upgrade perhaps in a few years.
Yep.
All right, great. Our next question is for Haiyan from Anthony on YouTube, who asks, once the Electron Ion Collider is up and running, how long until you produce that 3D picture of the proton?
Oh, that's actually a very, very good question. So how long? I think that with everything we are doing with AI, ML, and computer, and a lot of talented students, scientists, I think that maybe in several years, and we started to have this kind of pictures. And then as we continue to take more data, and the picture will just become a movie, okay? So initially we will have pictures, and then we will have enough pictures so we can make a movie. So several years.
Thank you. So we have a lot to look forward to, it sounds like, in all these areas of research. Okay, our next question is for Allison via email. What kind of research is your team conducting on tree canopies? This is interesting. The scale of your climate research goes from on the street in the city to tree canopies and then also clouds in the atmosphere. So how about what's happening in the tree canopies?
Yeah, that's good. So our plant physiologists focus on the very small scale structures within leaves to understand, how photosynthesis works and how that changes when the environment around the plant changes. So when temperature changes, how do those processes change? And when those processes change, they impact how much carbon dioxide is taken up. So what our terrestrial ecosystem researchers do is they try to understand these processes in a range of different canopy types. So they work in different regions across the globe, from the high latitudes to the equator, and try to understand, are these processes, is there something about these processes that are similar amongst all of these different plant types? Or are there things that are specific to different species of plants? And can we use that information to build a better predictive model?
Fascinating. Thank you. Okay, we have spent a lot of time going through all these amazing questions, but I have one last question, and this is for each of you. If you would please share one thing that you're most excited about for the future of your area of research. We'll start with Haiyan, followed by John, and then Allison.
So I think that the exciting thing is really to understand, the structure of visible matter of the universe. And that is what we do, experiment at RIC and also future EIC. But I think that in the end, we also wanted to really understand, the entire universe in terms of matter, right? Also dark matter and the dark energies. And they are also related, because in order to look for new physics beyond the standard model, we really need to understand everything within the standard model, and strong interaction, structure of visible matter is a very important part of that.
Thank you.
Kahil, you can't choose between your children. I can't choose between different areas that nsls-ii does and pick one. They're all exciting. I love them all. So I thought my answer would be more along the lines of, what I'm excited to see here is building capabilities that allow us to tackle problems with many different techniques at the same time. We call this multimodal, more than one technique at once. And so building the data infrastructure that allows you to combine different data sets from different beamlines to tackle one problem. That might be energy storage, or it might be biology, where you look at something over a range of different length scales and combine all that data together to have a really complete picture of that one problem. That's really exciting to me, and that will cover many different ranges of science. So that's what I'm excited about for the future for nsls-ii.
Yeah, that sounds like it would be a distinct and unique advantage to collecting all this information when you do your experiments at the different beamlines. Right, Allison?
Yeah, so I think for me, it's the prospect of being able to evolve our observational paradigm in atmospheric and climate science. So one of the biggest challenges we face in building a good predictive climate model is bridging scales. So I've talked about how we study these things at very small scales, aerosol particles and their properties, cloud droplets. But what we really want to know is how changes in these things affect the larger climate on, a global scale. And it's difficult to connect those two things. And the way we've made measurements really tells us about one or the other. And I think where we're headed now is to really fill this knowledge gap by building a new observational paradigm that will inform us directly about how these scales are related to each other. And I think it's going to be exciting to be a part of that, and that Brookhaven is really well positioned to contribute to that.
Yes, it sounds like we certainly have a lot to look forward to and amazing future discoveries to be had here at Brookhaven. And I want to thank you all again, Haiyan, John, Allison, for spending your time with us today. I want to thank all the viewers who tuned in and joined us and asked incredible questions. Thank you so much for being a part of this conversation and spending part of your evening with us. If you'd like to be notified about upcoming live stream events from Brookhaven National Lab, please visit www.bnl.gov/live-events. And I'll be signing off and saying thank you. I hope you have a wonderful evening. And we really enjoyed our time today.
Night, everyone.
Thanks all.